Welcome back, everybody, after lunch. My name is Anselm Schultes, and I'm the session chair together with Tobias Geiger over there and Sven Willner for this next session called Counting Economic Costs of Climate Change. I would like to take just a minute here to kind of frame what you can expect from the next 1.5 hours. We plan to cover 4 aspects of climate impacts here, roughly aligned with the 4 talks you will now hear. So, firstly, in order to count climate damages, you need to know what's there, what's out there. So the first talk by Ilan will deal with what we can observe in damages easily, but also with what usually goes unobserved, of the consequences of extreme events. In a second talk, then, it's more about adding up these damages and assessing their long-term consequences. And Shardul Agrawala from the OECD will talk about that in more detail. Adding up these impacts, you need to weigh them against what else goes on in society. And a popular measure for that is the social cost of carbon. David Anthoff will talk about the next generation of social cost of carbon assessments in a third talk. And fourthly, one needs to make scientific results available and accessible to society in general in order to facilitate planning and also response to extreme events. And Holland, in a fourth talk, will elaborate on that. So without further ado, I would like to ask Ilan on the stage. Ilan is the chair in the economics of disasters at Victoria University at Wellington in New Zealand. So Ilan, the stage is all yours.
So thanks the organizers for inviting me. So I'm an economist. I'm sorry about that. I apologize. But it is what it is. I'm happy to be here. I think it's interesting to do this in Potsdam, and I'm sure that people from Potsdam have heard this before. But Potsdam, to a large extent, shaped the second half of the 20th century, right after the Potsdam Conference. So it's interesting that maybe we're part of shaping up the rest of the 21st century, thinking about this topic. Okay, so I'm like the friend from the colleague from Egypt that earlier asked. I'm also a climate ignorant. My work is on disasters, mostly on sudden onset events. And not necessarily climate events. So some of the examples that I will use are not climate events, but I think the general patterns that I will try to describe apply both to climate, to weather sudden onset events and to other types of sudden onset events like earthquakes, which coming from New Zealand is my favorite topic. So the question I am asking is a very simple one. What are the socioeconomic impacts of large disasters? Okay, it's a simple enough question. Typically, when we think of how disasters affect society, we talk about the immediate impacts, and then we talk what happens later. And Stefan, I don't know where Stefan is, but Stefan, talked about the socioeconomic resilience, which is essentially an attempt. I know he doesn't like the term, and I agree with him. So, we can call it a tomato. But the question is how that tomato, what happens to society after the event and how it affects society over time. And over time, I mean both in the short run, and I'm not really clear about what I define the short run, and potentially even in the very long run, permanently. And I know that Keynes observed that in the long run we're all dead, but even taking that into account, we have a lot of evidence that large disasters have even an impact on the next generation. Okay, so that the impact of a single event can even transfer across generations because one generation is disadvantaged, and because of that disadvantage, it translates into losses into even a future generation. So we are really talking about something very long run. So The immediate impacts, we measure them, these are the stocks, right? The stocks of stuff that we lose, and of course, the mortality that is experienced by large events, the morbidity, all these immediate impacts, and of course the assets, right? The infrastructure, the housing, the roads, the electricity networks, the water, all of these things that are being damaged during a sudden onset event. Okay, I want to make two observations about these sudden onset, about this direct impact on assets. One is, I think, easily seen in this figure. Most of the damage to assets from disasters is in high-income countries, okay, by far most. So if you compare low-income countries to high-income countries, and I'm colorblind, so I have no idea what colors these are, but this color, whatever it is, what is it? Gray. And so the gray color, I hope you're not colorblind. The low income, the damages in low income countries are, in high income countries are 25 times or sort of something like that, 25 times as high as in low income countries. But of course, that's not the right metric. The right metric is to look at what happens to, what is the magnitude of these assets relative to the resources that are available in the economy, right? And that's the other color. We'll just call it the other color. The other color, you can see that the loss in low-income countries is actually about 20 times higher than in high-income countries, right? And Stefan mentioned some part of that today when he talked about really the big numbers don't really mean anything because the big numbers are here, but where it actually means something is here, is in the low-income countries. Okay, so that's the first observation about the direct impacts. The second observation is actually taken from David's comments in the last session before lunch, and that is that he doesn't want to attach dollar value to life. So what we are doing here is doing exactly the opposite, attaching life value to dollars, because dollars are worth life, right? The assets that we lose because of a disaster have an impact on our well-being, okay? So what we do here is we adopt this concept from public health. Somebody mentioned that in the morning session of the DALY, the Disability Adjusted Life Years, and we compute the total losses associated with both the number of people killed, the number of people affected, and the damage to assets in the Philippines. This is just an example. I chose one country. I could have chosen any country because we've done this calculation for all countries. I chose the Philippines for two reasons. I want to make two observations here. One is, if you look at the overall amount of life years lost associated with disasters in the Philippines, most of it is because people are affected, right? It's not because of the damage to assets. The Philippines is a low middle income country, so then the dollar value of assets that is lost is not very high, but a lot of people get affected by disasters in the Philippines. It's mostly associated with floods and with cyclones, tropical cyclones. But if you look at the graph, most of the damages is from the number of people affected. I do want to note that this doesn't include, the graph just stops before the year in which the Philippines is hit by Haiyan, by Typhoon Haiyan, which was very, very destructive and also caused a lot of mortality. So this is even without Haiyan. But the second observation I want to make, and this is why I chose the Philippines, is that you see that the last decade or so was pretty bad. And why is it interesting? Because in the Philippines, Philippines is usually taken to be a model country in its development of disaster risk reduction measures and disaster risk management measures. Okay, they passed probably one of the more sophisticated laws about disaster risk management. They have a very sophisticated ministry that deals with, relatively speaking, very sophisticated attempt to deal with this, but still they haven't been able to deal with the problem, and the problem seems to be growing. And if that's the case, the Philippines, then of course think of other countries where their disaster risk management policies are much less advanced, then of course it is much worse. Okay, so these are two observations about the stocks, but what we're interested in more, I think, and I know Stefan is more interested in that, and that's the flows. What happens later? What happens to that? We called it a tomato, right? So what happens later, both in the short run and in the long run? So typically when we think about that, we think of possibly 4 stories, okay? The best one is that this leads to some creative destruction, right? So there is some destruction available, but then that leads to beautiful new infrastructure being built, and we're all good. This is a unicorn. That doesn't ever happen. But the 3 scenarios that we do need to think about is the scenario of Build Back Better. We frequently hear about this Build Back Better aim or goal. Or we can think of recovery to trend or no recovery at all, where we end up with somewhat lower trajectory. And if that lower trajectory is permanent, then if you integrate that over time, we are talking about very, very, very big impacts. Okay? So among economists, the usual assumption, and this goes back centuries, literally centuries, so I could have used a quote from Adam Smith if I wanted to. He has a quote in the Wealth of Nations about this, but this is from John Stuart Mill. And John Stuart Mill observes that we basically recover. So what is surprising for him is the great rapidity with which countries recover from all these shocks, the earthquakes, the floods, and hurricanes. So the standard assumption, if I go back here, the standard assumption among economists is that we have recovery back to trend. Okay? But if we look at the literature, actually the literature mostly finds that we don't have recovery back to trend. Okay? There is one paper, Cunhado and Ferreira, that finds that this Build Back Better scenario, this optimistic scenario, does materialize. But before you get all excited, they find it only for floods, only for agrarian societies, and only for very moderate floods. Okay? So it's not really something we should get too excited about. Okay, so the point I want to make is that the devil here is always in the detail, and every disaster is a bit different, and that's where we need to think about, we need to examine case studies. This is an earthquake, the Kobe earthquake in 1995. What we observe in Kobe, and I'm not going to explain the whole thing, but the point is that Kobe experienced permanently a decrease in income per capita of 15%. Permanently. 20 years later, and we're now 20 years later after the earthquake, in my estimation, the income per capita in the city is 15% lower. So if you integrate that over time, this is a humongous loss. 2 points I want to make about these long-term trends. Two issues that may be driving those trends, those long-term impacts. One is the impact on institutions. I'm going to skip this because I don't have time, and I'm going to give you an example in a minute. The other one is the impact on confidence. Confidence is a very important driver in economic activity, and especially in investment decisions. So if for whatever reason these shocks decrease confidence in the viability of our society or institutions or whatever it is, the services, the infrastructure, whatever it is, then we may have very, very adverse long-term impact, and that is a big concern. I have a few examples here which I can share with you, but I'm going to probably skip both. Well, the top one is the Meiji Restoration in Japan. So the Meiji Restoration is the period of industrialization in Japan in the late 19th century. It started after a series of big earthquakes. The big earthquakes led to this is one story, led to a loss of confidence in the government, and because of that, the government decided that they have to change something, and they opened up and they modernized and so on. So we can have sort of these stories where these changes in institutions lead to positive outcomes. But typically, what we observe that the changes in institutions lead to worse outcomes. And the drought picture there, of course, is from Syria, right? And we know that the Syrian drought is at least a component of what happened in the horrific things that have happened in Syria in the last several years. Okay, why should we care about this? Well, largely because if we want to do anything about policy, we need to understand the economics. We need to understand the science. We need to understand what we can do about the science, so the planning and the engineering and the mitigation. But we also need to understand the economic impacts, because that will help us assess the costs and benefits that are associated with whatever action. And without that, we cannot derive policy decisions. Sorry. So the question is, in the long term, what is the counterfactual? What are we comparing ourselves to? So if you look at what the Cheshire cat answers Alice, it basically tells her, well, if you don't really know where you're going, then it doesn't matter. You'll get there. And am I run out of time? 30 seconds. Okay. So one way to deal with this is adopt the approach of this Buddha statue and just take it easy and not worry about the long-term impacts. I don't think this is the right approach. I think that economists are not really good at forecasting, and this is an example of this kind of failure to forecast. John Kenneth Galbraith said that economic forecasting was invented to lend some credibility to astrology. And we're not very good at that. But I think what I get from these nuances about what is happening, the various possible scenarios that can happen after an event, is that a lot of the impacts are in the long term and are not very easily observable. And if they're not very easily observable, we need to really think deeply about how we plan our policies to prevent them. Yeah, that's it.
Thank you very much, Ilan. There's room for a couple of questions, so please step forward.
Okay.
Yes, please. Just. No clue what kind of alarm that is. Anyone who knows? Well, we can try to ignore it. It's not too loud. So, why don't we take the first question? Over here, maybe? All right. Please go ahead. Are you?
No.
Just.
We're just holding the mic.
Okay, there's nobody. Right. I'm sorry, I understand. So there's no question in the audience. So there's one over there. Stefan?
Defining this, I should stop screaming, this synthetic Kobe, or like these baselines, assuming that the event did not occur, is something that might be very relevant for the impact research in general, about the definition of those baselines that we're using, and we're comparing things against baselines which are just model-based and we don't really know what they mean, but everything is measured compared with them. So I was wondering if you had looked at how these approaches that you develop for natural disasters, how they could be used for climate change impact research, so for much longer term baseline definition.
So these synthetic control methods are retroactive rather than prospective, right? So we cannot use them to forecast future impacts. We could potentially apply them to look at past impacts of sudden, but mostly I think they're appropriate for sudden onset events. So I have several other works that have looked at various other other cases. And this is part of what I mentioned sort of at the end there. So I have one paper that looks at a hurricane in Hawaii and what happened there. And in that hurricane, most of the economic activity in this island was based on tourism. The tourism infrastructure was destroyed. People lost their jobs, moved off island. So the island lost about 15% of the population. Somehow 15% seems like a magical number here. But lost 15% of the population permanently. Now, if you ask people today on that island what they think about this, they said that's the best thing since sliced bread. Because, the population is smaller, there's less tourism, the tourists are, everybody hates tourists, except when you are one. And they're happy with that. So loss of population is not necessarily a bad thing. It could be a good thing, at least depending on who you ask. So what I'm trying to drive at is that it's a very complicated sort of decision. What the right counterfactual is a very is a decision that will affect, and this is a point you made, I think, earlier, is that what we choose to measure affects what the solutions we find. And that's an important insight there.
Yeah,
Right.
thanks, Ilan. Just one question, I'm back here. One question on this index you had for the Philippines. You said, okay, they are one of the best doing in disaster response and disaster management, but still they have this increase. So, but what is your take on that? Is it climate change that happened, or is it in the Philippines, or is it rather they should even do better, or what is missing?
My interpretation of this is that, yes, it is climate. And typically when we talk about cyclones and climate change, we talk about the change in intensity and the change in frequency of events. But what is happening in the Philippines is the change in the trajectory of cyclones. And the cyclones are now moving south in the Philippines. They're hitting more the southern provinces in the Philippines. And the southern provinces are less accustomed to that. So they're less able to, they have lower socioeconomic resilience, to use Stefan's lingo. So they have less tomato. And because of that, we have this increasing. So yeah, I tie it to climate change.
Thank you very much. I think there's one more question over here, but we're out of time, so please keep it very quick.
Okay, yeah, thank you for your presentation. My name is Matthias Kalkul from MCC Berlin. You said that there is different evidence on whether there is recovery or not. I was wondering whether we know what influences the speed of recovery. Is it the role of capital markets, the institutions which support reinvestment? So do we know anything about this? How fast recovery will be?
We know surprisingly little about that, actually. In general, recovery is not something that has been researched that much, especially recovery in the long term. There's some research on recovery in the next, the first few months, what happens after the first few months. So the short answer is no. We do know that the availability of resources matters, and that the availability of resources can be remittances, or it can be insurance, or it can be the ability of the government to mobilize or to borrow money, or and things like the ability of households to borrow money. And so these things matter, the availability of resources matter. But beyond that very general statement, we don't know much. And I think that is a productive avenue for sort of future research.
Okay, let's thank Ilan again. And the next speaker on stage is Shardul Agrawala. He is the head of the Environment and Economy Integration Division at the OECD Environment Directorate in Paris.
Good afternoon, and thanks for having me here. I'm also going to start with a confessional. I'm going to follow Ilan's precedent. My confessional is I don't work on climate anymore, and for the past couple of years. And this happened after the financial and economic crisis, where a lot of people asked the economics profession, why didn't economic models see it coming? I think Queen Elizabeth posed that question to her team. But a lot of international institutions, including the OECD, also had that exercise in examining our analytical models and trying to see how we can upgrade them. So I got involved in that process. And subsequently, I came back to environment, but I have a broader set of responsibilities looking at resource efficiency, regional trade agreements, but also looking at overseeing some of the work on macroeconomic modeling. Climate is not directly there, but it's sort of at the back. So when I get invitations for climate talks, my first response is avoid. But Anselm and his team were very, very, very persistent. So my next response was adapt. And then I spent, some time between midnight and 2 o'clock to just dust off the cobwebs. So what you have here is not my work. It's a review from a bit of distance now at this field on quantifying economic consequences of climate change over the past quarter century in 15 minutes. So there'll be broad brush strokes, but hopefully you'll get the big picture. There's a very interesting workshop right after that where you have the real experts talking about it. So very quickly, first, it's in 3 parts. First, I'll be reviewing briefly early approaches to quantifying economic impacts. So I'm putting them into 3 categories, what I'm calling enumerative approaches, then looking at integrated damage assessments, and then finally coming on to what many of you might be familiar with, which is the parameterization of damage functions within integrated assessment models. Then I'll come to newer approaches. They're not really new, but newer. And there are 2 tools which are being increasingly used, also to come up with aggregate estimates, computable general equilibrium models, and empirical panel estimation using weather shocks. And finally, I'll conclude with some thoughts on reconciling findings from these approaches and some thoughts on the road ahead. So very quickly, looking at early approaches, I was reading, this is the paper which started the field, Nordhaus, 1991. And he opens it with the section, we now move from the terra firma of climate change to the terra incognita of social and economic impacts of climate change. So in this paper, and that's the paper, he looked at what bottom-up studies, primarily in agriculture and sea level rise, were saying about biophysical damages, and there were some economic analyses at that time, and then he made certain extrapolations and came up with estimates of economy-wide impacts. And then he tried to extrapolate to the rest of the world. This was followed by Bill Klein, 1992, who looked at more sectors and followed a similar approach. And there were a couple more studies, and then there was this, it was Sam Fankhauser's PhD thesis, which became a book, which had more international coverage and looked at a lot of more sectors. Now, I'm restricting this talk to aggregate estimates, but bearing in mind that they rest on the shoulders of this really extensive work on biophysical impacts, including what we heard this morning. And in the early 1990s, I mean, I'm glad to see people like Cynthia Rosenzweig in the room, the work, the YASA studies on agriculture that she did. I mean, a lot of that work was feeding into the economic analyses, which were then aggregated upwards. So what did these approaches do? I mean, the total damage is a sum of these individual categories. They didn't look at higher order adjustments, for example, through changes in prices, benchmarked for a climate which is this focus on doubling of carbon dioxide equivalent concentrations from pre-industrial levels. Underlying information dominated by US studies, primarily in agriculture and sea level rise. By the time we got to Fankhauser's study, a lot more sectors were being looked at. And they were looking right from the bat, actually, on market and non-market damages. This is a table from Fankhauser, 1995. And you can see there are a lot of impact categories, even 22 years ago. I mean, there's coastal defense and agriculture and so on. But you have dryland loss, wetland loss, forestry, fisheries, there's nothing, it's listed, energy, water, morbidity, air pollution, migration. It's quite surprising because many of those topics are now coming back again. Obviously, it was drawing on the literature that existed at that point, but the economists were thinking about some of these categories. Now, then we come to integrate, I must also mention, so Nordhaus's first paper said the aggregate impact on the US economy would be 0.25% of GDP. And then he said, okay, add up, taking into account the fact that there are plenty of damages which are non-market damages, let's make it 1%. And then he came up with a range of 0.25 to 2%. And as I'll tell you later, that range hasn't changed that much in the years since. So the next category of approaches is these integrated damage assessments, they're more comprehensive, and they also look at market adjustments through changes in relative prices. But they ignore non-market damages. So there were two very interesting early assessments in the 1990s. There's this famous, this is the first instance where I'm talking about more regional assessments as opposed to global. There was a study called the MINC study, Missouri, Iowa, Nebraska, Kansas. And they used a very interesting approach. Instead of using projections of climate from GCMs and all the challenges with downscaling, they looked at a real analog of the Dust Bowl years of the 1930s, where temperatures were about 1 degree warmer, and they had data on all the impacts and interactions between the impacts, and they used that as a proxy for climate in 2030. And then they looked at how individual sectors were impacted and used input-output tables to measure economy-wide impacts. A second study in 1993 actually used general equilibrium modeling. This was a paper which was submitted to a YASA workshop, which looked at the economy-wide impacts of climate change in the US, largely focused on agriculture, energy demand, and sea level rise. They used a very extreme scenario for mid-century, 5 degrees warming, but the impact they came out with was relatively modest, 0.8% of GNP. Now we come to integrated assessment models. This is the paper by Nordhaus. This is the model. He had two papers in 91 and 93. This is the DICE model, and this is where he came up with the damage function within integrated assessment models. And there's been an industry of IAMs in the last 25 odd years, all of whom, or the ones which look at damages, use functions provided by, I think I'm still correct, these three models, the DICE-RICE family, or the Page model and the Fund model. And there are some differences, but you're essentially looking at the loss function, which you take off from GDP as a function of, some function of temperature. Nordhaus has a quadratic function. Now, the difference is Fund sort of aggregates up from the region and sector level, whereas Page and DICE-RICE are multi-sectoral. I think Page also has a regional focus. In recent years, or over the past decade or so, there's also been progress in adding adaptation as a policy variable. And I think the work of Kelly de Bruin in particular in doing some of that work is quite important. Now, these are some of the results. This was a paper, a synthesis paper that Richard Toll had in 2014. You have the scenario for warming, impact at the aggregate level as a percentage of GDP, and then some information on the worst off and the best off regions. So roughly you're talking about for 2.5 to 3 degrees, it's negative 2.5% of GDP. Worst off region, the 95 study looked at was 8.7% in Africa and 0.7% for Russia in terms of benefits. This is a more recent paper which Nordhaus came out with in 2017, where he looks at a warming of 3 degrees and 6 degrees. And for 3 degrees, it's roughly in the same range, negative 2.1. And for 6 degrees, it's negative 8.5. So people have written, people can write PhD theses on that, but I'm just going to summarize it on one slide. I think there's been discussion about IAMs in general and the damage functions since the 1990s, and there are plenty of critics of it. But a lot of people continue to use it, and they use it from those three sources which I mentioned. One of the reasons is what I'm calling the plug-and-play simplicity of using these functions in integrated climate economy analysis, particularly if you're doing a longer-term assessment over the end of the century, for example. The second thing is relative simplicity and flexibility. For example, if you think we need a different functional form for higher levels of climate change, you can change the polynomial and put, instead of a quadratic function, you can put a higher order function, and people have done that. And you can sort of, whatever your assumptions are about the future, you can put it in and get your results. But there are a number of problems. I think two of the key problems are you get little insight on the channels of transmission of economic impacts, and there are questions about the underlying theoretical and empirical basis of these damage functions. Perhaps the strongest critique came from Robert Pindyck at MIT in the context of the debate on social costs of carbon. This damage function is made out of thin air. It isn't based on any economic or other theory or any data. Even if this function were somehow the true damage function, there is no theory or data that can tell us the value of the parameters. Now, recent approaches have tried to address these two limitations: insights in terms of the channels of transmission of economic impacts and deepening the empirical underpinnings of what we say about future damages. So the first category of approaches I'm talking about is CGE modeling, computable general equilibrium models. They combine economic models with very detailed information on sectoral activity and linkages between sectors with information from climate models as well as empirical literature on climate damages. They're modeled with a production function, and then you're looking at how climate shocks impact different components of the production function and can explain how composition of GDPs changes over time. They can capture the heterogeneity of climate impacts better than reduced form IMs. And they can also look at impact on growth rates, not just levels of growth. But on the other hand, they can capture a smaller subset of impacts. They cannot handle non-market damages. They're much more complex and generally suitable for a shorter horizon than IMs. The more heroic CGs have gone mid-century or 2060 in the study we did, for example. So some recent papers, a lot of them came out of the group at FEAM in Venice, and building on a lot of their work, we did this analysis on economic consequences of climate change, which came out in 2016. What we did here is more than CGE. We modeled what we could within the CGE framework, but we also looked at things which we could not incorporate through standalone analysis, and we looked at fatalities from heat waves, urban damages from river floods, and also tried to get a handle on biodiversity loss. What we couldn't do is look at large-scale disruptive events. Just one slide on the result. You can see the regional granularity in terms of our results. This is looking at impacts of climate change. I think 2.2 degrees is the central projection at that point, and we're looking at the impacts across a whole set of countries. Then now what we're doing is we looked at how do the impacts change if we take the range of climate sensitivity from 1.5 to 4.5 degrees, and you see the axis, the vertical axis of damages has changed. You can get higher impacts. And if you take the full range of IPCC's climate sensitivity, go up to 5.5 degrees of climate sensitivity, then you have countries like India, for example, hitting close to 12 or 13% of GDP by mid-century. So the impacts certainly are a lot more significant once you take at least one of the key sources of uncertainty into account. Now, coming to newer approaches, which are the empirical studies. Empirical literature has always been there, but a lot of it, until recently, was cross-sectional. And there has been a lot of literature which has shown a strong negative relationship between hot climates and incomes per capita. In the climate context, there were a series of studies what were called using the Ricardian approach, which actually showed zero impacts or even net benefits as a result of climate change, because they were superimposing what would happen as a result of a warmer climate in one place with what was actually happening in another region which had a warmer climate, and there were plenty of challenges to that approach. But that was the debate between the empiricists and the modelers in the 1990s. I'll show you very quickly how the debate has changed. Now, panel estimations using time series data for a given location and looking at the impacts of weather shocks on the economy is much more recent. You can sort of take away many of the other variables which might condition outcomes and get a stronger causal link. There have been studies focusing on average weather, extreme events, specific impact categories, very few global assessments. The first global assessment I'd like to mention is out of a team at MIT, which looked at the past 4 or 5 decades of temperature shocks and economic growth. What they concluded was that for low-income countries, there is a negative impact. There has been a negative impact on economic growth as a result of these temperature shocks. For rich countries, the result is statistically not significant. What they caution is, given uncertainty over adaptation, technical change, and other issues, the estimates here, driven primarily by short-run fluctuations in temperature, alone cannot provide predictions about the estimated impacts of future climate change. The next study does precisely that. So they basically show that overall productivity is nonlinear in temperature across all regions and over the time frame they looked at, and then they used that relationship to project impacts into the future. And the impacts are unmitigated warming is expected to reshape the global economy by reducing average incomes by roughly 23% by 2100. Average incomes in poorest 40% of the countries would decline by 75%. Those are the regional results. I'm not sure you can read the vertical axis, but for some of the regions, it's much higher than 75% of GDP per capita. So how do we wrap up? I'm getting to the wrap up now. So if that's the elephant of economic consequences, what I've discussed is essentially shedding three beams of light to look at these consequences, and there are plenty of linkages between these approaches. They're not as discrete. Can we reconcile the findings of this? First of all, I mean, the bottom line messages over the past quarter of a century from enumerative approaches, IAMs and CGs, have been remarkably sticky, roughly a couple of % of GDP for 2 to 3 degrees of warming. Now you have this new literature which is pointing to dramatically higher impacts. There is a concern that IAMs, we know the limitations of the IAMs, they also exclude large-scale disruptive events. The question is, has there been a premature anchoring around some of the earlier results, and that's led to this quote-unquote consensus? But at the same time, this new empirical analysis, first of all, it's very nascent, there are relatively few groups, and the bigger question is, can one really extrapolate the economic consequences of climate change from the impacts of data on unanticipated year-to-year weather shocks? That's the central question, which at least I have not seen convincingly answered yet. Some thoughts on the road ahead: greater scrutiny and benchmarking. I think the poor damage function has had plenty of scrutiny. We know its limitations. Not sure that's the case. We haven't shed the light on empirical approaches yet. Greater cross-fertilization, how to use this rich empirical literature to better parameterize, for example, the damage functions in IMs or feed into CGEs. We need to also question whether aggregate economic outcomes measured through GDP losses is the right way to go. Should we focus on distributional consequences and well-being? Stefan was making this point. But also, we need to recognize the limits of these tools, particularly in terms of their ability to shed light on the true game changers. This is partly Pindyke's argument. Ultimately, the real game changers would be what John Schellenhuber was talking about this morning, the likelihood of truly disruptive and catastrophic climate events. What is the likelihood of them, and what would be the economic consequences? Nobody knows, but that's one of the game changers. The other game changer, I would say, is the fundamental economic structure is also changing right now as a result of digitalization, and how would climate and economy interact in the future, I think, needs a broader look than just a focus on how these interactions took place in the past. So, final recommendation, we also need to look at softer approaches like expert elicitation and foresight and analysis. Thank you very much.
Thank you very much. Right, there's like 2 minutes for questions, so please step forward. Ilan.
So it seems to me that the biggest issue in terms of the climate impacts is the distributional issues. So some countries are going to gain, some countries are going to lose. And the distributional issues and the politics of the distributional issues seems to be the big elephant, not so much the aggregate. So are we losing the important picture by looking at these aggregate numbers?
Thanks for that question. I think there are two aspects of distributional issues. One is distributional effects across countries, and that disparity has been pointed out by a lot of studies in the past 2 or 3 decades. But there's also disparity in terms of impacts within countries, and that's been less looked at. I absolutely agree with you. There have been studies which have done that. But there is still this fixation, I don't know where it comes from, in terms of looking at the percentage of GDP number. I'm not sure if that's what the policymakers want or what the research community thinks this is what the policymakers want. I don't know, but there is this perception that you have to boil it down to percentage of GDP and come up with one headline estimate.
Thanks very much. So I'd like to ask David Anthoff onto the stage. David is a professor an assistant professor in the Energy and Resources Group at the University of California at Berkeley. David, stage is all yours.
All right, thank you for having me. It's great to be back home. I'm German, so I just left the country 7 years ago. And what I thought I would talk about is, I'll give you a little bit of an update of what's happening across the Atlantic in the US, and especially what's happening about social cost of carbon estimates there. So the first part of the talk, I will just set the stage a little bit and give you an update about federal policy and in what way economic work has shaped that over the last decade or so. And then I will give a bit of a roadmap of what I think should or will happen with social cost of carbon estimates as we go forward. So the first thing to note about US climate policy is that most of what we've seen over the last 8 or 9 years was driven by the courts and was located in the executive branch. So all the attempts by Congress to do anything about climate change have essentially faltered, and all the action has been in the executive branch via direct regulation of the economy. And really there have been, in my mind, 3 major things that happened that pushed for that situation. So the first one was that in 2007, there was a lawsuit that ended up in front of the Supreme Court, and the Supreme Court ruled that greenhouse gas emissions are pollutants as defined in the Clean Air Act, and that required the EPA to figure out whether they actually endanger public health or safety. So the statutory framework for US climate policy is the Clean Air Act from the 70s that Nixon imposed. So EPA started that process, and in 2009 came out with what's called the endangerment finding. And EPA looked at all these scientific evidence, and they found that elevated concentrations of greenhouse gases endanger both the public health and the public welfare of current and future generations. And this is sort of a landmark finding in US climate policy, because people at this point think that it's very, very difficult to undo this finding. But if EPA came to that conclusion, the regulatory framework almost forces them to do something about climate change. They can no longer say, oh, I'm just going to ignore this is not happening, or something like that. So those 2 events were really important. And then a third setup of the US administration, or the US regulatory environment, are various executive orders. The first one was issued by Ronald Reagan and then renewed by Bill Clinton. It's the Executive Order 12866. And what it says is that as the executive branch plans regulation, if that regulation has a major impact on the economy, and that's defined as more than $100 million per year, then they should do a cost-benefit analysis of that regulation. Now that cost-benefit analysis is not binding, but it should inform the process of coming up with regulation. So if you take those 3 things together, then there was a situation for the US government where, in essence, they had to value the impacts of climate change in their cost-benefit analysis. And when the Obama administration came into power, they looked at that situation and decided, okay, we need some metric to quantify the benefits of any change in greenhouse gas emissions that any regulation might impose, so that we can incorporate that into our cost-benefit analysis of regulation. So what did they do? They decided to use the concept of the social cost of carbon for this step. The social cost of carbon, most of you probably know this, is defined as the expected marginal damage of an additional emission of 1 ton of CO2 into the atmosphere. So it's the net present value of all the harms that 1 extra ton of CO2 that you put into the atmosphere is expected to cause over the next couple of centuries. That gives you a unit value per ton of CO2 emission, and then you can simply multiply that value with any changes in emissions and get a measure of the benefits of your regulation. So how has this been used? It has been used in a lot of federal rulemaking in the United States over the last 8 years. So there are dozens and dozens of regulations where the social cost of carbon was used in the cost-benefit analysis of that regulation. It was both used in regulations that didn't specifically target climate. So there were, for example, regulations of vending machines for soda drinks, And they felt that that would change emissions in some sense, and then they valued those changes in emissions with a social cost of carbon. The impetus for that regulation was not climate policy, it was something else. But it was sort of, that's how deeply embedded this is now in the US regulatory process. But there were also regulations like the Clean Power Plan, which were the major pillars of US climate policy. And all the climate benefits in the regulatory impact analysis for the Clean Power Plan were quantified by using the social cost of carbon estimate. How did the US government go about estimating the social cost of carbon? They used 3 integrated assessment models. Integrated assessment models, most of you probably are very familiar with that, are models that combine insights from multiple disciplines, and you can use them to estimate the social cost of carbon. So they used 3 of those, actually the 3 that you mentioned, DICE, Page, and Fund, to come up with an official US federal social cost of carbon. And in the last administration, that was about $40 per ton of CO2. Over the last 8 years, the social cost of carbon, this concept, has spread out into a much wider area than just federal regulatory impact analysis. So that's one area where it was used. But by now, lots of states in the United States are using the social cost of carbon in their regulatory process. So they have officially adopted the social cost of carbon concept into their procedures. There are a couple of other countries that have adopted and followed the US lead on social cost of carbon use in their official regulatory analysis, for example, Canada. The number that has come out of this official US federal process has its own life at this point. So for example, this spring, a group of conservative thinkers came up with a proposal for a carbon tax in the United States. And the tax rate that they recommended was $40 per ton of CO2, which was clearly taken from the social cost of carbon estimate that the federal government had been using. So there's sort of an intellectual history at this point of this work. And then there are lots and lots of court cases where the social cost of carbon in the United States, where the social cost of carbon has figured quite prominently, where courts have told folks you cannot argue that you cannot value the benefits of climate change because see, the federal government is doing it. You can just use the same number. So in some sense, this concept is now really deeply embedded in the federal rulemaking and public policy world. All right, so now I'm going to give you an update about the current situation and what the Trump administration is doing. That is actually hot off the press. It was literally released yesterday. So I read everything this morning and I hope I got everything right. So what the Trump administration is doing right now is they're trying to repeal the Clean Power Plan rule. And they have a new regulatory impact analysis about the Clean Power Plan rule that in their mind argues that, that this rule should actually not be promoted. And in that new regulatory impact estimate, they actually still use the social cost of carbon estimate. So they have not done away with that in their regulatory process. But they changed the social cost of carbon that they use in two key ways. The first one is that they changed the discount rate that was used to estimate the social costs of carbon. So instead of using a 2.5%, 3%, and 5% discount rate, as the previous administration has, they're now using a 3% and a 7% discount rate. So overall, those of you who are familiar with discounting, this will lead to smaller numbers, especially the 7% discount rate will lead to much smaller numbers. The second change that they did is that they moved to what we call a domestic social cost of carbon. So the previous administration used a social cost of carbon that aggregated all the benefits across the world into the regulatory impact analysis of the United States. So if the United States decided to build a cleaner power plan, then they would count the benefits to someone here in Germany as a benefit in the regulatory impact analysis in the United States. The Trump administration did away with that and is now using a purely domestic benefit estimate. With those changes, you get a new social cost of carbon estimate of $6 for the 3% discount rate and $1 for the 7% discount rate. So, and as far as I can tell, nothing else has changed, which is quite, so, I mean, I'm not a, but it's, which is quite remarkable. So there's no change in the attitude towards the climate science that underpins any of this. There's no change in the attitude towards the impact estimates that underpin any of this. So in some sense, if you take what came out yesterday as the official position of the Trump administration on climate policy, then they are actually, at least with this work, not questioning climate science or climate impact work. They're really just, which is dramatic enough, changing how those things are aggregated. Okay, so that's sort of my brief Trump update. The previous administration, looking forward, asked the National Academy of Sciences in the United States to write a report with recommendations what we should do next about the social cost of carbon for policy work in the United States. So the National Academy of Sciences assembled a committee. Those are the folks that were on this committee. It's a very distinguished group of people. And they came up with a long report in January that outlined their recommendations of what a next generation of social cost of carbon estimates should be. I'm not going to go into the details of that. I'm just going to cover one aspect of that today. Currently, there's probably an expectation that the administration might not pick up these recommendations. But there's another effort that I'm really excited about. It's spearheaded by Resources for the Future, the think tank in Washington, D.C. And UC Berkeley, in the form of me, is part of that. And we're starting a very large-scale project to implement these National Academy of Science recommendations. The Sloan Foundation provided really welcome seed funding for that, and so we hope that this is going to be a really large-scale effort. So let me highlight one issue with the social cost of carbon policy process in the United States. So essentially you have all this climate science and impacts research area here out there. It's a large and vast literature. Then you have a very small number of cost-benefit integrated assessment models, namely 3, that estimate the social cost of carbon that then influences federal policy. In some sense, these 3 models are gatekeepers for all the climate research as it influences the regulatory process in the United States. Those 3 models are built by very small teams. So DICE is built by Bill, Nordhaus, Page by Chris Hope, and FUND is built by Richard Toll and myself. But that's 4 people that wield a lot of influence over what actually makes it into the official federal number, which is probably not, I mean, it's great for me, but it's probably not a good and robust setup in terms of policy advice. So one aspect that the RFF project that we're really trying to focus on is to improve this pipeline from all these other studies into the social cost of carbon estimates that might be used at the federal level. So some of the goals we have is we want to get more experts involved in building these integrated assessments that then actually inform the federal policy. So we want to widen the group of people that work on this. We want to provide a lot more transparency about the models that are used to estimate this by breaking them essentially up so that they're no longer sort of black box models that the 4 of us understand and no one else. And then we want to create a closer loop between the people that built these integrated assessment models and the larger science community that provides the insights that we are trying to replicate and represent with these integrated assessment models. So the strategy for this, and this was one of the strategies that the National Academy of Science report recommended, is that what we have currently is we have individual integrated assessment models that combine insights from all of these different areas. And what we want to do is we're going to break this up so that we have what we call a common software platform, and then these individual parts of an integrated assessment models ideally will be built by decentralized teams so that it is no longer 1 or 2 people that try to do everything, but that we can sort of spread this out. And that a research group that, for example, only works on climate science can build a component or module on this common software platform about the climate science part, and then it will link with all the other modules that we're going to create. So one part of this project is building this common software platform, and then hopefully lots of people will come and contribute to this effort so that their work makes it into the number that informs climate policy in the United States. I'm going to rush over the next part a little bit. So my group at Berkeley, we have been working on this kind of vision for a long time. We've created a software platform called Mimi. I'm going to skip over the history here. The goals are exactly what the National Academy's report proposed. So we want to enable this decentralized workflow. We want to increase transparency. We want people to be able to run experiments on these models and say, if I take the damage function from Page, combine it with the climate model in Fund, what do I get, right? So that we get a better understanding of which parts of the models drive these things. I'm going to skip this one here. Just a quick update here. We've done a lot of work. All of these models that run on this Mimi platform have been broken up into their individual parts, and you can mix and match them. Lots of them are not released yet because we want to publish at least one paper with them, but then they will all be open source and publicly available. We've also had really good success working with other groups at this point. So there's a group at Princeton, at Penn State, and they're adopting this platform. So we're making first steps in actually getting this out of a small group that sort of is centered around a single person. So this is our effort there. Okay, so I have one last slide, and then I'll stop. So this is sort of a Lego for integrated assessment models that we're trying to build here. I think a much more, or a very interesting question is, what do we do if after that we still have conflicting evidence about things? And the last talk highlighted that really well, right? So we have evidence about impacts that is really quite heterogeneous. So one thing is that this modular approach might help us to better understand these differences, and we might identify areas why those differences actually shouldn't be as large. On the flip side, I actually don't think they will go away. I think that's sort of not where we are at this stage in the game. So I think one really interesting future research area is rigorous approaches that deal with these vast differences in estimates. And there's a literature about ambiguity aversion, and there's sort of a theoretical literature that's really interesting. One question that I have is how can we make that accessible enough so that it can be used in policy advice settings? Because some of that literature is very theoretical and complicated, and how can we bridge those insights with a real-world policy-making setting? Okay, my conclusions. The social cost of carbons is really the main vehicle in the United States to get scientific evidence into the regulatory process. And so my call to action is engage with that, right? So if you want your work to be reflected in the federal rulemaking process in the United States, then try to integrate it with social cost of carbon work. Thanks a lot.
Thank you very much, David. There is a first question over here.
Yeah, thanks for that, David. I think it's a great vision, this open source vision you have. In the spirit of that, there's a paper led by your former colleague, I'm sure you're familiar with it, Fran Moore, that shows by updating just the agricultural damage functions in Fund, your model, it doubles the overall social cost of carbon, which is low in Fund. Mm-hmm. Can you tell us, is this going to happen in all the other areas? Do you think bringing new science to bear is going to result, even at 7% discount rate, in a much higher social cost of carbon? What are you thinking is likely to come out of this massive open source approach?
So the work you mentioned with Fran is a key. So Fran has been really involved in this whole process. She's a very close friend of my lab. So I hope that we'll see, and so what she did is she updated the damage function for agriculture and found very different results. We hope that this kind of process will happen for all the other damage functions as well. If you look at the damage functions in these integrated assessment models, they're all old. If you trace back when these damage functions were created, it's before I started, most of them were created before I started in this field, which is not a good sign. Because I've been around for a while. So we hope that that will happen for other sectors as well. Fran's work is, and you're part of it, right? Sort of you're a co-author. We actually hope that that is sort of one of the models of, that other groups will emulate. One good thing about this work specifically was that it was a different group. It was not me or Bill Nordhaus or someone else who did that work, right? And that's the workflow we want to get to, that we're not the gatekeepers for this kind of work. So yes, I hope that other folks will do this. I will not speculate whether other updates will increase or decrease the social cost of carbon, because I simply don't know.
Great presentation. I have a question in one sense, simple sense, about terminology. So there are other models that are called integrated assessment models, you know, GCAM, et cetera. And I'd like you to just elaborate a little bit on what you think of the differences between those two different approaches, yours and the general ones that you've described and the other ones. But secondly, this whole idea of providing the plug-and-play approach to modules, I think, is really important. And 21st century approaches to this using what the CS folks have been in business for a long time would be really valuable to make it easier for you to borrow from the GCAMs of the world and vice versa. So the second part of the question is, say just a little bit more about the technology that you're using in terms of going to open source.
Yeah. Okay, so so integrated assessment models are a very broad field. The way I look at this is there are what I call cost-benefit integrated assessment models. So those are models that cover both the costs and the benefits of climate policy. And those are typically, so the major ones of those are the three ones that were used by EPA. So DICE, Page, Fund, I think which can do this at this point as well. But those models tend to be relatively simple. And the benefit you get from them is that you can combine sort of everything. There's a whole other world of much more complicated integrated assessment models, the GCAMs, the merges, and they have not really played in this social cost of carbon game. I think a lot of them are hesitant to put out social cost of carbon estimates, maybe wisely, who knows. But I wish they would enter this area. I think some of these groups are thinking about it or were thinking about it because they saw how important that channel is in the US, at least for federal policy. So that's how I divide the world. It's actually quite ironic because the social cost of carbon doesn't need the cost side of these integrated assessment models. It only uses the impact estimate side of these cost-benefit models. But for better or worse, it seems to be the cost-benefit analysis models that come up with these social cost of carbon estimates. Okay, so something about this modular platform. So this is actually the third time that I'm trying this. So I broke up, this is my third time that I'm trying to build a computational platform like this. The main criterion I have is that it has to be simple. Because if you have to deal with 10,000 C++ files and then 15,000 XML configuration files, and it takes you 2 weeks to even just run anything, we lose half of our audience. So the main focus that we have this time around is actually make it so that people can ramp up very, very, very quickly. And the other thing is performance. We need something that is really performant still, because some of these modules are computationally intensive. I think I'll leave it there. If folks are interested in more technical detail, then I'm more than happy to chat. I'll be around.
Let's do that. Thanks very much. Thanks, David, again. So next and last speaker in this session is Greg Holland, who's a senior scientist at the Mesoscale and Microscale Lab of NCAR and a director of the Capacity Center for Weather and Climate Extremes.
Thank you very much. And I'd also like to both thank the organisers for letting me speak, and especially Tobias for having let me know about this conference. It's actually quite a fabulous meeting. What I'm going to be talking about is is tools and an approach to presenting tools. Am I up there? I'm not. It's here. There it is. Tools and an approach to actually presenting those tools that we've developed over the past several years. The focus is entirely on climate and weather extremes, but I'll emphasise the timescales. We go from about seasonal out to multi-decadal. So when I'm talking about weather extremes, I may be talking multi-decadal. Weather extreme is not what happens tomorrow. It depends on the scale of the system. Why do we do this? And I'd also, like to acknowledge my other collaborators in this particular activity. Why do we do this? It was because we're all researchers, and we were actually starting to talk to a number of different societal groups, and we realised just how little information they were getting, and we also realised, at least I did, just how bad I was at actually communicating information to them. And I think you'll find that that's true in a lot of cases. So here is what's been happening over the past few decades. This is from Munich Re, and it's the number of different natural disasters with the types showing up on there. Our understanding has increased a lot. Our ability to forecast has increased a lot. They've kept going up. They've kept going up for two reasons. Three reasons, actually, but I'll start with the first two. The first one is that there is simply more people. There's more people also moving into more exposed areas, so vulnerability has gone up. Vulnerability's gone up, resilience has gone down as a result of those movements. The other component of this, which is hard to dig out, but it's sitting in there, is the fact that the climate has been changing. As you've heard before, climate change is not in the future. We've already got it, at least some of it, and there's an element of that in there, and in some cases a very large element of that in there. And the final reason, coming back to my original comment, is that the work that we're producing has not been getting to those people necessarily. So we formed a group called the rather large name of Capacity Centre for Climate and Weather Extremes. We didn't form it because we wanted to just simply say, let's go ahead and do it. We held several community meetings in several different countries before we actually made our mind up to go down this path. And the whole purpose of this particular activity is to take knowledge, data sets, experience, and all the other sorts of information that's in this group and in many other groups around the world, and make it very easily accessible in a form that's useful for people in the street. People in the street I'll define as Indigenous groups, multinational companies, local city and town planners, and farmers, and a whole range of other sort of people that actually need to be able to use this information. So we're not going through the formal sort of international structures and everything to do this. We're trying to get directly to those people. And our ultimate goal is to decrease vulnerability and to increase resilience as a part of this activity. A few comments on the principles that came out of these meetings that brought us to this point. Firstly, when you do something like this, provide what is needed, not what you think is useful. To say another way, most people say what they want to say when you should be saying what they need to hear. And it's amazing if you can just get that thought into your head, how differently have a perspective on life. We were working with Native American communities. It took us 3 years to the point where they would actually even talk to us. But once we got to that point, we couldn't shut them up. They kept on, they were wonderful. The second one is we work on nation, state, city scales, global as well, but nation, state and city scales. And I have a number of my modelling colleagues, including I bet quite a few in this audience, say, you can't possibly be providing information on the city scale. Well, guess what? People are making decisions on the city scale, and if you don't provide them with any information, they have nothing. So we provide what we can. Not say we can't do it, we say what can we give them in that, on those sorts of scales. And actually, as you'll see a little bit later on, it is actually very easy to provide information on these scales if you're just careful about it and reasonably good at doing it. Uncertainty and confidence. We rarely talk about uncertainty, we talk mostly about confidence. Same word, same thing. But it is too easy to say, oh my goodness, well this has got all that problems, it's got this and everything else. And by this stage people have said, well they don't know anything, so why should I listen about it? But if you say, our confidence in this is low or our confidence in this is high, not only is it useful information, in the case of a lot of groups, they can make a lot of very valuable progress out of just understanding that confidence level. A company can make money out of understanding the confidence level. A farmer can make money out of understanding the confidence in the seasonal forecast. And finally, we operate on a principle of graceful failure. Every time we're talking to someone, we actually talk to them on the basis of don't plan to build the building, plan what you're going to do when the building falls down. Then go ahead and plan to build a building. And the point here is that things are going to fail anyhow. Things are failing on a daily basis. It's a bit silly to just simply build it and say, well, worry about that when it happens. But once you actually have this graceful failure concept, it's amazing how a lot of these uncertainties and things up here start to actually disappear because it's no longer critical if the building fails or the dam or whatever else it is. you've actually got a plan in place and you're able to actually take that information into your planning process. So with that, we have built a thing called the Global Risk Resilience and Impacts Toolbox. I think built is a little bit too premature. We have the components together, but we're still putting them, we have the components, we're still putting together, and I'll demonstrate some of those. If I start at the bottom, there is an enormous amount of data out there, climate data, modelling data, seasonal forecast data, vulnerability data, etc. We're gradually gathering information on where those are and using them as we can find them and as we can get access to them. We don't store it ourselves, it's just way too much. So we have a framework with an engine that operates in the cloud that actually when you need some information, it goes finds it, does the computations locally in the cloud and only sends back what you need. We also have an extremely sophisticated visualization system. We didn't invent it, we work with a company called Tableau, who have I have to say, an absolutely unbelievably good visualization system. You can just play with it and get information back out of it. You'll see a few examples. And then we have community tools. We've developed a few, our colleagues have developed a few, and as time goes on, we see this growing and growing and growing. A bit like apps on the iPhone, if we've got the rest of the system there, people can build tools that actually are useful to them or useful to colleagues or just something they'd like to have go out to the world at large, and we will maintain it. And the final point here is that this whole engine supports both the societal people, but it also supports research activities because you can use this to do your own research. So let me show you a few examples, and that's all I'm going to do is show you a few examples and then I'll stop. This was one that was developed for the construction industry in the United States. We talked to them for backwards and forwards for about 6 months, and it turned out I went in thinking, oh, they're going to need all this really, really difficult information. The only information they wanted was, can you tell me in 3 months' time what the likelihood of the wind being higher than a certain value, the temperature being higher or lower than a certain value, and the rain being higher than a certain value at a place like Chicago? I mean, it's absolutely trivial. They do not have that information. It's $1 trillion business, and they don't have that information now. So this is what we did. We put it together under Tableau, and you can see in this case, it's exceedance of 30 degrees C, and it's all those little squares and things of the counties across the US. Gives you an overview. We can then dig down into, say, California, and this shows you how the system works as well. We have up on the top left-hand side the average Tmax for the period that you're looking at. You have the days exceeded for the number you've chosen. You have the confidence, and we have the raw data sitting across there, so you can actually look at them and you can download those and take them away if you like. Up in the top right, you'll see a date. You can actually change the period you're interested in. And down the bottom right is the threshold, and you can change the threshold that you're interested in. In this case, it's been set at 85 degrees Fahrenheit. If you click on, say, Marin County, or just hover the mouse over Marin County, it comes up with these sorts of information. So you've got a little bit of information on it, or you can click on it, and now we're only looking at Marin County. And it gives you, again, the temperatures that occur in that particular time frame, along with the number of days exceeded and the confidence. And confidence in this group, they weren't interested in PDFs, so they get confidence, which is just simply days exceeded. 1/3 of the model said that was it, 2/3 of the model said that was it, or 3/3 of the model said that was it. That's medium, high, and low. So I'm going to finish up with two more, actually. I'll easily fit that into the three. Firstly, we go a little bit more sophisticated. We have a global tropical cyclone catastrophe model and a wind footprint. And here we took a model developed by someone else, updated it, and now we have a very sophisticated boundary layer model so we can handle very complex wind fields. Everything we do when we're talking about tropical cyclones is in terms of damage potential, not maximum winds or something like that. And we also have a hybrid numerical tropical cyclone model, and I'll finish up by showing you those three for this talk. Here are the footprints from that footprint model for actual hurricanes that occurred around the world, just showing you a bit of a global viewpoint here. We can zoom into a couple of them, and you can see over here we have Wilma going through Florida. Over there we have Haitong going through Taiwan. And you can see the detail that you get in the wind field across the land simply because we've got a good boundary layer model. Notice how the winds accelerate over Lake Okeechobee. There's not much topography there. We then go to Taiwan, which has got very high mountain ranges, and you can see the enormous impact of topography. And this is information that is not available and has not been available in the past. This system takes a lot of expertise and a lot of computer time to run. So what we're doing is we're producing entire data sets, so when you actually go and access it, you don't run it, you just access the information, so it's more like a grab and visualization of the information. I'll pass that one over and, no I won't, I'll go through it. The cyclone damage potential includes intensity, size and translation speed. Intensity can be a good number. Translation speed you wouldn't think was useful, but it's critical to the whole process because it's how long the winds blow, and size is both how big an area. And here I've got just a few from the 2005 season showing up here. The size is the size of the cyclone, and the depth of the red gives you the value of the damage potential. I can again click on it and I'll come up with Katrina and it gives you the relevant information. So let me ask you a question. What was the cyclone with the most damage potential for 2005 for the United States that made landfall? It wasn't Katrina. Katrina was number 4. Katrina was a human disaster. It was not a natural disaster. It was a disaster because we had actually screwed up badly. And we screwed up all the way down the line. That's why there was so much damage done to New Orleans. And I get a little bit upset when I hear people describe these things as natural disasters. The last one I'm going to show you is 3 slides which show you the rainfall. Here we have a version of the weather research and forecast model, and this requires a lot of expertise to run. But again, we're providing it to people with expertise, and we're providing the data with those that don't have the expertise. What you see is the rainfall. The white is the highest rainfall going down through the colours for a cyclone that it's a made-up cyclone coming into the Australian east coast in a past climate control situation. We had 2 degrees global warming, and you'll see that the rainfall is extended well down the coast, and here is a few catchments that I want you to latch on. So Burnett River, Richmond River and Hastings River. They're shown across the top. We have the normalised rainfall per catchment, so area and that doesn't come into it. And you'll notice a quite amazing thing. The black line is the original run. The other ones are various sensitivity studies, but the red line, for example, or the orange line is the climate change run. There was actually less rain where the cyclone came ashore, but look at the enormous amount of rain that occurred further down the coast. Well, it turned out that a year after we did that work, there was a cyclone came ashore in a not dissimilar place with over a degree warmer conditions than normal. And this is the rainfall from the Bureau of Meteorology for that month. 62 stations had record rainfall. 62 locations had record rainfall in this particular cyclone, and it is one of the largest damaging and disrupting an insurance losses system that Australia has ever experienced. Not because of the winds, not because it was a particularly interesting cyclone, because the water was so darn warm and there was so much warm water and you had a mountain range up there, it all drove it in a non-linear fashion into a massive national disaster. And I'll stop there, and if you've got any more questions, I've got a bunch more slides I can show you. We have tools which cover hail, actually do hail very well, large hail. We have tools which cover severe rainfall, not tropical cyclone rainfall, and various other things, but we'll talk about that offline. Thank you.
Thank you very much, Greg. There's a couple of minutes for questions. Ilan.
Maybe it's a question that might not interest too many other people, but I'm curious how you got the insurance companies to play ball with you on this.
It's called 25 years of trying to get it happen, and then suddenly it happened. The thing about the insurance companies is if you go back 10 or 15 years, they were anti a lot of this stuff. You know, they had their own people and they wanted to do it their own way. Well, they've actually completely turned around, and the financial regulations that are being imposed on the world, including themselves as part of it, their shareholders are starting to say, wait a minute, what are you doing about climate change? So we now actually get, it's not great money, but it's in the hundreds of thousands of dollars a year, money to do both this, but also to do research. They actually pay us to do some fundamental research if it's information that they actually need. And it's not just them, we're actually starting to get a lot of money out of commercial companies in general, simply because they're starting to recognise it's in their interest to actually do this. The hard bit is getting money to support people like American Indians, who no one wants to spend any money on any of those things.
Thanks. There's another question over there.
Oh, sorry.
Hi, my name is Carol Song from Purdue University. I'm curious on who are your users of your platform, and what kind of expertise they would need to have to put their applications in there.
If you go to our website, which is not up there, it's just do C3We at UCAR or at NCAR, and you'll find it. You'll find they're listed there. We show a list of just one of these rolling sort of lists that show people. They vary from companies. There's an awful lot of commercial activities are involved, to local cities. We have a very big program with Indigenous people, which we have to support ourselves because they don't have any money. And we also have commercial companies, including the insurance company, but also various other groups. So it works across that range of things. And we have a number of researchers, actually quite a large number of researchers, that are starting to use the system, but also that are actually starting to contribute to the system. The whole idea is this is a community effort. I can run through a whole list of names if you like. You would have seen a bunch of them on the slides as I went through as well.
Thanks. Then maybe one quick question from my side. You
Yeah.
mentioned that for, like, in talking to many of the organizations and let's call them customers of yours in the last years, it took quite a while to get in touch with them. Is there like a single reason that stood out as the most important one in preventing or making communication hard, or was it very diverse?
It was a combination of things. I'll finish up by telling you how we actually go about it. If I go talk to an insurance company, and then the next day I go talk to an energy company, and the next day I go talk to the chief of a tribe, and we may be speaking English, but we're speaking completely different languages. And it took me, at least, a long time to realise that you have to speak their language. So if I'm looking at a company that's profit-making, I don't go in and tell them about doom and gloom. I say, you know, you can make money out of this, and suddenly you got their attention. Or the regulatory authorities are going to be coming down on this. You've got their attention. The other thing was that we just needed to actually build up a trust base. And we did that by running things which we call the Engineering for Climate Extremes Partnership workshops. We run them around the world. The next two, if you're interested, are in February, and one's in Hong Kong and one's in Australia, in Sydney, Australia. And in those we have local researchers, local stakeholders across the whole board come in, and we just get them talking to each other, and then we get ideas out of that, and then it goes on from there. So that's how we do it.
Thanks very much.
Thank you.
So let's thank Greg.